Hey everyone, welcome back to my channel. So far, we have studied several neural network or deep learning models for forecasting, such as fully connected network, and then like the recurrent networks such as LSTM, and the more recent ones, we studied NBits, NBitsX, and NHITS. In this video, we're going to study another type of deep learning that is transformer-based. So we're going to study a transformer-based model for long-term forecasting, and it's called Informer. More specifically, we're going to see how an input is processed from the very first layer to the very last one. And as usual, we will employ this model to a dataset. Okay, let's study together. Okay, so this is the complete architecture of Informer. Like I just mentioned earlier, Informer is a transformer-based model, so it has the two same big parts, the same basic architecture, that is encoder-decoder architecture. Inside the encoder and decoder is a self-attention mechanism. Notice that we have three types of self-attention mechanisms in Informer. The first is multi-head ProbSparse self-attention. The second is masked multi-head ProbSparse self-attention in the decoder part here. And the last one is multi-head attention. The last type here is the same multi-head self-attention mechanism as in the transformer. Okay, now let's focus ourselves on the encoder. The encoder part consists of several layers, several encoder layers, and this count as one layer. So the white and the thin blue trapezoid is count as one layer. Each layer has two subparts. The first is a multi-head ProbSparse self-attention, and the second one, illustrated by the thin trapezoid here, is the self-attention distilling operation. And then the output of the encoder would be a concatenated feature map. So the role of an encoder is to capture or take features from an input. And then that feature map is fed into the decoder part, but that's not the only input a decoder receives. The decoder also receives what it's called the X decoder. We'll get to that later. But the point is that the decoder will receive its inputs and then process them, and the output of the computation process would be fed to a fully connected layer before generating the output. Okay, now let's get into the detail of the model, starting from the input of the encoder. Okay, so let's say that we have our full data like this. Informer can receive multivariate or univariate time series, by the way, okay? But what I'm illustrating right now is a univariate time series. Okay, so let's say that this is our full data. Then the input would be just a window or a subsequence of length Lx. In the coding section later, Lx is called sequence length, seq_len. So yeah, I might use both terms interchangeably. Anyway, this window is fed into the model, and the first thing that the model does is input representation. We have three types of representation: value embedding, positional embedding, and time embedding. For the value embedding, the features are extracted via a convolution layer. The total filters or kernels that are used in that layer is the output dimension that is denoted by d_model or d model. We'll get to that in a minute. And the kernel width is 3. So that's how they extract the features of the values themselves. Okay. And then for positional embedding, it takes features from the index of the value. So the indices would be put into a sine or a cosine function depending on whether the index is an odd or even number. For the time embedding, it's basically taking features from the timestamp. So the informer will take the timestamp in the dataset, and from there they work on getting the timestamp or the frequency that we have, and they will learn the features from the timestamps. It will be clearer in the coding section. These encoding layers have the same dimensions, and Basically, that's depending on the total features you want to take in the value embedding. We denote that dimension as d_model or d model. So the output of the input representation layer is a matrix that is called, as written here, x encoder. So x encoder at time t. T is like the tth subsequence. Okay, and the dimension of this matrix is Lx rows and D model columns. Then X encoder at time t will be fed to the encoder part. This diagram shows the complete left part here, the left part of the informer model. So the green array here is the time series itself. We have two shades of green here. The top array is the scalar, so it's the time series itself, and the bottom array is the timestamp. And oh yeah, I forgot to mention that in the input representation layer, there's also a convolution operation. Okay, but this part is the input representation layer that we just discussed. Okay, so next let's move on to the attention block, or as written in the diagram, multi-head ProbSparse self-attention. Okay, let's start from the last phrase, self-attention. So self-attention is an attention function that is used to map the queries to a set of key and value pairs. This is what it looks like mathematically. To describe this function in words, it is a weighted sum of the values, that is the matrix V here, where the weight is the softmax of the scale dot product between the query and the key. The dot product of Q and K is scaled by 1 over the square root of dt is the input dimension. So in our case, that would be d_model. Because the input of the self-attention layer is the output of the input representation layer. Okay, now let's go to the second phrase, that is ProbSparse. So what is ProbSparse self-attention? It's basically a self-attention, but only for some dominating queries. So the dimension of the matrix Q bar and matrix Q are still the same. It's just that now matrix Q bar is a sparse matrix. Okay, so now the question is, how can we decide which queries are dominant? I'll try to describe this briefly. So first of all, there are only U dominating queries in matrix Q bar, and that's defined as the log of the total rows of matrix Q times a factor. The default value of the factor is 5. They prove in their paper that generally 5 is the best value for the factor. And we take the U dominating queries by comparing their query sparsity measurement. That score is denoted as M. M bar, we have this bar sign indicating that this value is actually an approximation. So yeah, in summary, to get a sparse matrix Q bar, we need another approximation. The core motivation of Informer is basically trying to reduce the computation cost that is imposed by the transformer. So the transformer has a quadratically cost, and that's because in self-attention, as in the transformer or as in the last part on the decoder here, the operation is including all the queries and all the keys. And we want to avoid that as much as possible. And you can see that this part here, the one that's inside the softmax function, is exactly the same as in the calculation of the query sparsity measurement. See here. So to avoid using all queries and keys and having quadratic cost of computation, we have to approximate the query sparsity measurement. The informer does that by first randomly taking some keys and multiply them with all the queries, getting all the query sparsity measurement, and then just take the top U queries, and those are our dominating queries, which then would be used for making the sparse matrix Q bar. In other words, those dominating queries would be left untouched in the matrix Q. So let's say that we have our matrix Q earlier here. That's our original matrix Q. And then to make the matrix Q bar, we keep the dominating queries, but change the other rows to an array of zeros. So let's go back to our ProbSparse self-attention. If we look at this, the computation cost would only be a big O of Lk times the logarithm of Lq. But since in practice Lk and Lq is the same anyway, so we can reduce it to L log L. Okay, now the last bit of this layer, of this subpart actually, is the multi-head. So these functions are only for one head. But as stated in the transformer paper, it's better if we have independent projections to the matrices Q, K, and V. So that's why we have multi-head. More intuitively, multi-head allows the model to focus on a certain subsequence or a certain part of the input. Okay, let's move on to the next step. The output of multi-head ProbSparse self-attention would be a sparse matrix, right? Because matrix Q bar is a sparse matrix. And therefore, there will be many values of matrix V that are redundant. So to let the model focuses on the dominating features, we need a self-attention distilling operation. Okay, so let's see the computation that's going on in that operation. So the output of multi-head ProbSparse self-attention would go through a convolutional layer, and then the output of that would be put into an LU function, LU activation function to be exact. And lastly, it will be fed to a max pooling layer with stride 2. The fact that we use stride of 2 makes the output dimension reduced by half. Now, LU activation function is exponentially linear unit activation function, and it works like ReLU with an extra term alpha to accommodate the negative inputs. And the convolutional layer here is a convolutional 1D. So the convolution kernels would go for each head. So that's the end of the first layer. And then to make it more robust, we have another layer of encoder layer. And for the second layer, the input of that second layer is half of the input of the first layer. So this is why they draw a trapezoid pyramid. They want to illustrate that the total dimensions keep decreasing as we move further into the encoder. And lastly, the output of each head would be concatenated, and that is the concatenated feature map. Again, this is showing us the full process from the input to the last step of the encoder part. One little thing that I didn't mention earlier is that after two encoder layers, we still have one more attention block before getting the final feature map. But I guess in practice, in the coding section later, we won't apply this. So again, this is the input, and then this is the input representation layer, and then these two is the first layer of the encoder layer, and then this is the second. As we can see here, the dimension is L for the first layer, but for the second layer, it's L divided by 2. Okay, now let's move on to the decoder. We have just discussed how we get one of the input of the decoder, which is the concatenated feature map. Now let's discuss the other input, that is xdecoder. Xdecoder is an array. It's actually a concatenation of two arrays. X token and X0. Let's talk about the X0 first. X0 is an array and the length is the horizon. Obviously, we're not giving out the answer to the model, but we're just telling the model giving out the length or the horizon. So if our horizon is 10, that means we would have an array of length 10 and all the values are 0. In the coding section later, we will call the horizon as prediction length. Now for the X token, which is called label length in the coding section, it's about taking the start token. So this idea is adapted from the reading comprehension task. Let's say that we have a passage and then we have a question. We need to find the answer from the passage, right? And those models need the start token to mark the start of the answer. It's like the queue, actually, the way I understand it. It's like the queue before predicting the real outputs. Alright, so to reiterate, we've got our X token that has the length label length, and we have X0 that has the length of the horizon. If we concatenate them, we would get the X decoder at time t. Now let's dive into the decoder part. Okay, I'll just zoom in the diagram. So the decoder part has only one layer as illustrated here, and it has two sub-layers: the masked multi-head ProbSparse and multi-head attention. The additional word masked here is basically to prevent each position from attending the coming positions. In other words, the informer model wants to avoid autoregressive. Lastly, the output of the decoder is fed into the fully connected layer before generating the output. The output could be a univariate or multivariate time series, depending on our application. If you want to know further about Informer, especially about ProbSparse self-attention, I'll already give you the citation here. And if you're completely new to transformer-based models, then I suggest you to read the transformer paper as well. Alright, so let's specify the model now before training it. Yeah, maybe I should go over the cell first very briefly. So the first line is importing the .dictionary, and then the second line is for importing the experiment informer. So this is where the model lies. And then lastly, the model is written in PyTorch. That's why we are also importing Torch. We are going to collect all the parameters of the model into a dictionary. Actually, it's .dictionary. .dictionary is just like a dictionary, but we can get the value of the keys with just a dot instead of using square brackets and apostrophe. Okay, first we initialize the dictionary of parameters, and we call it args for arguments. Okay, and so now let's go over the parameters. There are many of them. First up, the model. Obviously, the model is informer. They provide some other options like informer stack and informer light, but we're going to go with the informer. And then the next parameter is data. Since we're using our own data set, so we go with custom. Okay, and then for the root path and data path parameters, we have actually defined this previously when we were in the custom data segment. Yeah, but I'm just rewriting it here because I want to collect all the parameters. And then the features parameter, this is about what our forecasting task is all about. We have three options, M, S, or MS. And we go with MS because our input is multivariate time series. That's the first letter is all about. And then for the second letter, this is for the output. S is for single or univariate time series. Okay, so it's MS. Okay, and then the next parameter is target. For this parameter, we put the name of the column in our data set that we want to use as our target. Since we want to predict the bond yield for the 10-year bonds, the name of the column is 10-year, 10YR. The next parameter, calls or columns, these are the columns that we want to use. Again, we have to put in a list of column names that exist in our dataset. The next parameter is the frequency of our time series. Our dataset has business days, so we put B in it. This model can accept many frequencies down to the second. Okay, but in our case, we will go with B. All right, and then the next parameter is the checkpoints. This is for setting up the directory where the model will be saved. And then the next group of parameters are about the input. So for the encoder part, the input is denoted as sequence length, and I set it to be 90. And then the output of the model is denoted as prediction length, and I set it equal to 21. So given 90 days of history, we want to predict for the next 21 days. And then the parameter label length is like the queue. So this is like the queue before the real forecast generated. Well, more formally, this is called the start token, and the length of the start token is 5. I just set it to be 5. I've tried other values like 10 and 21 and 0. And among those values, I think 5 gives us the best prediction. That's why I go with 5. And it's stated here in the comment that the complete input for the decoder part is a concatenation of the label length and prediction length. So the complete decoder input would be an array of length 26. Okay, next parameters. Encoder in and decoder in are the total variables as input. Now we take multivariate time series as our input, so it will be more than 1. We can set it to the length of the list of columns here. So that's why I set it like this. And then the parameter cout is, C is for channel, I think. This is the total variable as their output. We only want to predict for a time series, just 1, so cout is 1. Alright, let's move on to the next parameter, factor. The factor is 5. Here, recall that with ProbSparse self-attention, we want to take the dominant features, take the dominant queries, and to determine how many dominant queries we want, we use this formula. So the natural log of the total rows of matrix Q times C. C is the factor, and this is what this factor is referring to. The default value is 5, and we go with that. Next is d-model. D_model is the dimension of the model, and this is the dimension, the output dimension of the embedding layer. The embedding layer that we talked earlier when the data first go into the model. It's set to be 512, and we just go with that. Okay, and then n heads is the number of heads in the attention block. It's 8 by default. Okay, and then for E layers and D layers, they are encoder layers and decoder layers respectively. Again, I just go with the default here. So it's like in the diagram that we saw earlier, we have 2 encoder layers and 1 decoder layer. Alright, the next parameter is d_ff. This is the dimension of feed-forward network. And I just set it to the default as well, that is 2048. Alright, I didn't talk about this in the theory section, but in the ProbSparse self-attention, it's not only attention that lies in that part, but there's also the feed-forward network. Okay, so after the ProbSparse self-attention, we do a feed-forward network. And with feed-forward network, it's actually putting 2 identical layers. It's just the dimensions are different for both layers. So the output dimension of the first layer is the input dimension of the second layer. And that dimension is 2048. The type of layer that we're talking about could be dense layers like MLP or fully connected network, but it could also be a convolutional layer with kernel size of 1, and that's what they do in the code. A feed-forward network is also called the expand and contract network because they first expanded to 2048 and then contracted to the original dimension, which is 512 in this case. So yeah, the input dimension for the first layer is the same as the output dimension of the second layer. It's like the outer dimensions. So yeah, that's a little additional detail there. The next parameter is the dropout. It's 0.05 by default, but I double it to overcome the overfitting. Alright, and then the next parameter is the attention. We have two options, either prop, that is ProbSparse, or full, that is the basic attention mechanism. We're going to compare the performance that is generated from ProbSparse attention and full attention. Alright, the next parameter is embed. Embed is for embedding the timestamps. Okay, and we go with time f, that is the default. We have other options, namely fixed and learned. Okay, so recall that our data can be embedded in three ways: value embedding, positional embedding, and time embedding. The timestamps can be embedded in three ways: time f, fixed, and learned. Okay, so first of all, before going into the embedding layer, the timestamps is pre-processed. And this pre-processing includes breaking down the timestamps into some unit of times. In our case, since our data frequency is business days, the timestamps is broken down into 3 time units: day of week, day of month, and day of year. So the output of this little pre-processing is a time dataset, if you will, timestamp dataset of 3 columns. Now, with time f embedding, they will use this timestamp dataset and throw it into a dense layer or in linear layer, practically, and they will learn the relation between these columns using the fully connected network. And then for fixed and learned embedding here are quite similar because they are not putting the timestamp dataset into a linear or a dense layer. Instead, they are using embedding layer. Embedding in, this layer embedding here. So they will just build a lookup table of the time. Like they have the sizes for each unit of time. So for example, the minute unit of time has the size of 4, and then for hour has the size of 24. I guess that's because each day has 24 hours. And then after embedding each unit of time, the embedding results would be concatenated. It's just that with embedding, after they build the lookup table, they also set the weight. And this is where fixed and learned is different. The weight for the embedding lookup table is fixed based on the position of the timestamps. And then for the learned encoding, the embedding weight is learned automatically. Now, in our case, it's impossible to try the fixed and learned encoding, since to be able to apply these, our frequency of the dataset needs to be at least hourly. So any frequency lower than hourly, like daily, monthly, yearly, is not suitable for fixed and learned. Okay, so yeah, in our case, we have only one option, that is time f. Okay, the next parameter is the activation. So your GELU, Gaussian error linear unit. Okay, and this is the activation in the feed-forward network. All right, the next parameter is distill. This is asking us whether we want to use a self-attention distilling operation or not. And well, since this is one of the signature feature of Informer, so of course we want to use it. And then we also want to see the attention output, the attention matrix. We will see that later. So yeah, I'm setting the output attention parameter to be true. And then mix is also true. Inverse is also true because by default, our data will be normalized. So to get back our prediction, we have to inverse it. Okay, and then for these parameters, I just go with the default actually. MSE is the metric used here as their loss metric. And then for the rest of the parameters, what I want to point out is iteration and train epochs here. First of all, the iteration is 1 by default, but I'm going to set it to 5 because I want to see whether this model is robust. All right, and then the train epochs is 6 by default, but I'm setting it to 10. Yeah, so for the next parameters, these are just about whether we want to use GPU or not. Okay, so we have only one parameter left here, and this is actually probably the most important because this is where I modify the model. Okay, so the last parameter we want to talk about is detail frequency. Okay, and this is the frequency of our prediction dates. So here's how it goes. When we do prediction, we run the predict method. We will get a prediction for the adjacent dates that are outside our dataset. Now, since we have set that our frequency is a business day, by default, the detail frequency is also business days, and the model will generate the dates based on the business days frequency, which includes holidays, which is unrealistic, right? If you have seen my other projects in forecasting, like in LSTM project or in fully connected network for forecasting gold price, and hits actually, and hits for gold price, any forecasting projects that includes financial data, you will see that in those projects, I kind of ignore that we have holidays. I just pretend that the next data that are forecasted is for the next available day. And in this project, I want to stop ignoring that and really incorporating those holidays. So that's why I need to modify the model a little bit. I'm just adding a custom business day as one of the frequencies. That's all I did. So this is from Pandas. In Pandas time sets, we're talking about Pandas dealing with timestamps. With custom business day objects, we can set the holidays. And so when the dates are generated, they will exclude the holidays so that our data will be more realistic. Okay, and so how do I get the holidays? By the way, I named the holidays as holidays 25, and I got the holidays from the holidays library in Python. And I want to take it from the NYSE calendar, New York Stock Exchange. And for this line, well, what happened? So holidays 25, if you run the first line only, we will get that January 9, 2025 is also a holiday. It's a national day of mourning for former President Jimmy Carter. But it's actually an observed day according to the federal calendar. So that's why I'm popping this date out of the holidays list. And so yeah, that is my modification. Alright, now we can print all the arguments here. It's already listed here. The experiment, the object of experiment that we want to use is located in experiment_informer. So yeah, I'm just going with the default here.